Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Computer and Information Sciences, SOCIS, Postgraduate Diploma in Computer Applications, PGDCA, New, Semester 2, MCS, 207 Database Management Systems, Block-2 Database Normalization and Database Query, Unit-6 Higher Normal Forms, 6.0 Introduction. In the previous unit of this block, you have gone through the concept of single-valued dependency, called functional dependency, FD. Further, the previous unit discussed different forms of normalizations that can be arrived at by removing different types of single-valued dependency, viz. 1NF, 2NF, 3NF and BCNF. However, relational databases may have several other types of dependencies, which results in redundancy in a relation. Such dependencies thus causes the update anomaly, insertion anomaly and deletion anomaly in a relation. Therefore, more normal forms have been designed to address this problem. This unit focuses on the higher normal forms, namely fourth normal form, 4NF, which is based on the concept of multivalued dependency, MVD, and fifth normal form, 5NF, which is based on the concept of joint dependency. The unit also introduces you to other normal forms. For more details on other normal forms, you may refer to the further readings. In general, these higher normal forms are not very popular among industries. However, they propose good theoretical perspectives for the database design. 6.1 Objectives. After going through this unit, you should be able to times explain the concept of multivalued dependencies, times perform normalization up to 4NF, times explain the joint dependency, times explain the 5NF, times define other normal forms. 6.2 Multivalued dependencies. An attribute in a relational model represents only a single value information. How will you represent the information if a particular attribute is multivalued? Such multivalued attributes would require that information of all other attributes is repeated in an instance of the relation. This will result in multiple tuples in a single relation to represent information about one entity. The primary key of such a relation would be a composite key involving the primary key of the entity and the multivalued attribute. This situation becomes worse if an entity has more than one multivalued attribute. Such an entity will be represented by several tuples. The following example explains this situation. Example 1. Let us consider a relation employee.mp project tool. An employee can work on several projects and an employee has skills in several tools. Therefore, there is no functional dependency in this relation. However, this relation has two multivalued attributes, project and tool. The attributes project and tool are assumed to be independent of each other, as any project can use any tool. The following table, not relation, defines this situation. employee number, project tool, E001 DBMS, e-commerce Python, virtualization, E002 e-commerce, bank automation PostgreSQL, virtualization, E003 bank automation PostgreSQL, figure 6.1, sample data. However, to represent this information through 1NF, you need to create the following relation: project tool, E001 DBMS Python, E001 DBMS virtualization, E001 e-commerce Python, E001 e-commerce virtualization, E002 e-commerce PostgreSQL, E002 e-commerce virtualization, E002 bank automation PostgreSQL, E002 bank automation virtualization, E003 bank automation PostgreSQL, figure 6.2, 1NF relation of data of figure 6.1, This relation has no FD and primary key of the relation is composite key, E-hash. Project tool, therefore, the relation is in 3NF and BCNF. However, it suffers from the problem of redundancy. For example, the employee E001 is working on DBMS is appearing twice, so is that E001 knows the tool Python. This may lead to update anomaly. Further, you cannot insert information about a new employee who knows the tool's PostgreSQL but has not been assigned to any project. In addition, if you remove the employee E003 from the bank automation project, the information that E003 has skill in PostgreSQL would be lost. Thus, the relation suffers from update, insertion and deletion anomalies. How can you now normalize the relation as this contains no FD? For addressing the issues related to such relations, we may first define the concept of multivalued dependency, which relates to relations that contain more than one multivalued attribute. Let us define the multivalued dependency formally for a relation R, X, Y, Z, where X, Y and Z are a set of attributes. Multivalued dependency, MVD given a relation R, X, Y, Z, a MVD X registered trademark symbol Y will hold in relation R if, for a specific value of attribute set X, there is an associated set of values of attribute set Y, such that these multiple associated 0 or more values of attributes Y depends only on the value of attribute X. Further, values of attribute set Y have no dependence on the value of attribute set Z. Hence, if MVD X registered trademark symbol Y holds in R, another MVD X registered trademark symbol Z would also hold, as the function of the attribute set Y and attribute set Z is symmetrical. In the example 1 given above, the employee number can determine all the projects employee is working on, and also an employee number can determine all the tools in which that employee is skillful. Further, both the project and tool attributes are independent of each other. Therefore, the following MVDs hold in relation of example 1, E-hash registered trademark symbol project, E-hash registered trademark symbol tool. Let us now define the concept of MVD in a different way. Consider the relation R, X, Y, Z, having a multivalued set of attributes Y associated with a value of X. Assume that the attributes Y and Z are independent, and Z is also multivalued. Now, more formally, X registered trademark symbol Y is said to hold for R, X, Y, Z if T1 and T2 are two tuples in R that have the same values for attributes X. T1, X is equal to T2, X, then R also contains tuples T3 and T4, not necessarily distinct, such that T1, X is equal to T2, X is equal to T3, X is equal to T4, X, T3, Y is equal to T1, Y, and T3, Z is equal to T2, Z, T4, Y is equal to T2, Y, and T4, Z is equal to T1, Z. For example, consider figure 6.2. The two such tuples are tuple 1, E001 DBMS Python, tuple 4, E001 e-commerce virtualization. Then two more tuples must exist as follows: E001 DBMS virtualization, E001 e-commerce Python. Please check these two are tuple 2 and tuple 3 in figure 6.2. We are, therefore, requiring that every value of Y appears with every value of Z to keep the relation instances consistent. In other words, the above conditions insist that Y and Z are determined by X alone, and there is no relationship between Y and Z. Since Y and Z appear in every possible pair and hence these pairings present no information and are of no significance. Only if some of these pairings were not present, there would be some significance in the pairings. Note, if Z is single-valued and functionally dependent on X, then Z1 is equal to Z2. If Z is multivalued dependent on X, then Z1, Z2, the theory of multivalued dependencies is very similar to that for functional dependencies. Given a set of MVDs, say D, you can find D, the closure of D using a set of axioms. We do not discuss the axioms here. You may refer to this topic in further readings. Before explaining the 4NF of a relation, one more term needs to be defined. It is the trivial MVD, which is defined next. Trivial MVD, a MVCX registered trademark symbol Y is called trivial MVD if either Y is a subset of X or X and Y together form the relation R. The MVD is trivial since it results in no constraints being placed on the relation. For example, consider a relation dependent, E hash, a dependent hash. An employee can have 0 or more dependents, therefore, E hash uniquely determines the values of a dependent hash. However, this MVD is trivial, as E hash, a dependent hash, together forms the relation dependent. This dependent relation cannot be decomposed any further. Therefore, a relation having non-trivial MVDs must have at least 3 attributes. 2 of them would be multivalued and not dependent on each other. Non-trivial MVDs result in the relation having some constraints on it since all possible combinations of the multivalued attributes are then required to be present in the relation. In the next section, we discuss how MVD can be used to decompose a relation into fourth normal form, 6.3 fourth normal form. In this section, first we define the fourth normal form, 4NF, and then present an example about how MVD can be used to decompose a relation to 4NF. A relation R is in 4NF if for all the multivalued dependencies, X registered trademark symbol Y, any one of the following clauses holds times the multivalued dependencies, X registered trademark symbol Y is trivial, times X is a candidate key for R, the dependency X registered trademark symbol or X registered trademark symbol Y in a relation R, X, Y is trivial, since they must hold for all R, X, Y, in this case, R, X, Y is in 4NF. Similarly, if in a relations R, A, B, C, with only 3 attributes, if A, trivial MVD, A, B, registered trademark symbol C holds, then R, A, B, C is in 4NF. If a relation has more than one multivalued attribute, you should decompose it into the fourth normal form using the following rules of decomposition for a relation R, X, Y, Z. If it contains two non-trivial MVDs X registered trademark symbol Y and X registered trademark symbol Z, then decompose the relation into R1, X, Y and R2, X, Z, or more specifically, if there holds a non-trivial MVD in a relation R, X, Y, Z of the form X registered trademark symbol Y, such that X, Y is equal to F, that is the set of attributes X and Y are disjoint, then R must be decomposed to R1, X, Y and R2, X, Z, where Z represents all attributes other than those in X and Y. Intuitively, R is in 4NF if 1. All dependencies are a result of keys. 2. When multivalued dependencies exist, a relation should not contain 2 or more independent, multivalued attributes. The decomposition of a relation to achieve 4NF would normally result in not only reduction of redundancies but also avoidance of anomalies. Example 2. Normalize the relation MP, EHASH, project, tool, shown in figure 6.2 using the MVDs. EHASH registered trademark symbol project and EHASH registered trademark symbol tool. The relation has no FD but two MVDs. Therefore, the relation is in BCNF but not 4NF. To decompose the relation into 4NF, you may use any of the MVD. The decomposed relation would be MProj, EHASH, project, with MVD EHASH registered trademark symbol project, which is now a trivial MVD, and MTool, EHASH, tool, with MVD EHASH registered trademark symbol tool, which is a trivial MVD. On decomposition of the relation in figure 6.2, by taking the projections as stated above, the relational state of the decomposed relations would be, look at the screen, figure 6.3, decomposition of MP, EHASH, project, tool, relation to 4NF. You can observe the following in figure 6.3 times the key to relations. MProj and MTool are EHASH project and EHASH tool, respectively, times there is no redundancy in MProj and MTool relations, times both the relations do not suffer from any anomaly. So far, you are able to decompose a relation based on FD and MVD. Are there any other forms of dependencies? Researchers have shown several kinds of dependencies. However, for this course we will discuss about one more type of dependency called the joint dependency, which is discussed next. 6.4 Joint dependencies. As discussed in the previous section, a relation that suffers from insertion, update and deletion anomalies is decomposed using either FD or MVD. The normal forms require that a given relation R, if not in the given normal form, should be decomposed into relations to meet the requirements of the normal form. However, in some cases, a relation can have problems like redundancy leading to anomalies, yet it cannot be decomposed into relations without loss of information. In such cases, it may be possible to decompose the relation in 3 or more relations. When does such a situation arise? Such cases normally happen when a relation has at least 3 attributes such that all those values are totally independent of each other. It may also be the case when a ternary relationship exists among 3 entities. Following example explains this in detail. Consider a relation, ProjToolMP, projected, tooled. MPID, there are no constraints on this relation, that is, times any project can use any tools, times any tool can be used by any employee, times any employee can work on any project, times no employee would use all the tools, times no employee would work on all the projects, times no project uses all the tools, times all 3 attributes are independent of each other. Assume that the relation has the following relational instance: tuple hash projected tooled MPID 1P1 T1 E1 to P to T2 E to 3 T1 T2 E to figure 6.4, a ternary relation with all independent attributes. The relation above does not have any FDs and MVDs since the attributes projected, tooled and MPID are independent. They are related to each other only by the pairings that have significant information in them. For example, the first tuple of relation states that employee E1 works on P1 project, which uses tool T1. The key to the relation is the composite key, projected, tooled, MPID. The relation is in 4NF, but still suffers from the insertion, deletion, and update anomalies, as the information that employee E1 can use, tool T1, is redundant in tuple 3. Similarly, information like project P3 uses tool T1 cannot be inserted in the relation, as no employee has started working on the project. Likewise, on deleting tuple 2 from the relation, may delete the information like employee E2 can use tool T2. Therefore, you need to decompose the relation to minimize the anomalies. As there are no FDs or MVDs in this relation, there is no basis of decomposition. You may try to see what happens when you decompose the relation into the following two relations: project tool, projected to lead, P1 T1 P2 T2 P1 T2 project employee, projected emped, P1 E1 P2 E2 P1 E2 Figure 6.5, a decomposition of ternary relation of Figure 6.4. What happens when you take join of the two relations on the attribute projected, tuple hash projected to lead emped, 1 P1 T1 E1 to P1 T1 E2 3 P2 T2 E2 4 P1 T2 E1 5 P1 T2 E2 Figure 6.6, project tool join project employee. You may notice that the tuples 2 and tuple 4 in the relation state in Figure 6.6 were not existent in original relational state given in Figure 6.4. Thus, this decomposition is a lossy decomposition. So, what should be done to remove the anomalies? In such situation, you may have to decompose the relation into three relations, two of which are already shown in Figure 6.5. A third relation as shown in Figure 6.7 must be added to employee, to lead emped, T1 E1 T2 E2 Figure 6.7, the third relation. In order to obtain the original relation, you need to perform the following join operation: project tool join project employee join tool employee. Figure 6.6 represents project tool join project employee, which can be joined with tool employee, tuple hash projected to lead emped, 1 P1 T1 E1 to P1 T1 E2 to P2 T2 E2 4 P1 T2 E1 3 E1 T2 E2 Figure 6.8, project tool join project employee join tool employee. Please note that tuple 2 and tuple 4 of Figure 6.6 will not be part of Figure 6.8 as there are no matching tuples in Figure 6.7. Thus, you can observe that Figure 6.4 and Figure 6.8 are identical. Therefore, the relation pros-to-MP, projected, to lead, emped, which has no FD and MVD can be decomposed into three relations, which can be joined to form the original relation. This forms the concept of join dependency, which is explained next. Join dependency, JD. A relation R satisfies join dependency over the projections P1, P2, Pn, if and only if every instance of R, the join of P1, P2, Pn creates the instance of R. For example, the instance of ternary relation pros-to-MP, projected to lead emped, as shown in Figure 6.4, when decomposed to two relations, as shown in Figure 6.5, does not satisfy the join dependency. This is shown in Figure 6.6. On addition of the third relation, as shown in Figure 6.7, the three projections, project tool, projected, to lead, project employee, projected, emped, and tool employee, to lead, emped, satisfies the join dependency as join on the three projections, viz. project tool, projected, to lead, project employee, projected, emped, and tool employee, to lead, emped, is the same as the instance of the relation. Thus, the three projections, as stated above, satisfies the join dependency. 6.4 Fifth normal form. The fifth normal form, 5NF, project join normal form, PJNF, deals with join dependencies, which is a generalization of the MVD. The aim of the fifth normal form is to have relations that cannot be decomposed further. A relation in 5NF cannot be constructed from several smaller relations. A relation R is in 5NF if for all the join dependencies any one of the following clauses holds. A. Join dependency P1, P2, Pn is trivial, that is, one of the pi's is R. B. Every pi is a super key of R. For example, the instance of ternary relation pros-to-LMP, projected to lid, emped, as shown in figure 6.4, has a joint dependency. Project tool, projected to lid, project employee, projected, emped, comma. Tool employee, to lid, emped. Therefore, this relation is not in 5NF, as it violates the clauses of the 5NF given above. You can decompose the relation pros-to-LMP, projected, to lid, emped, into its projections as follows: project tool, projected, to lid, project employee, projected, emped, tool employee, to lid, emped. Each of these three relations are in 5NF as they have trivial joint dependency. The instance of each of the decomposed relations is shown in figure 6.5 and figure 6.7. You may also observe that this decomposition is lossless joint decomposition. It may be noted that every MVD is also a joint dependency. Therefore, every PJNF, 5NF, schema is also in 4NF. A relation schema that has joint dependencies and suffers from anomalies can be decomposed into projections. As per the joint dependency, the new relations would be in PJNF schema 6.5. Other normal forms. The researchers of database systems have found additional dependencies and normal forms. This section introduces the basic concept behind these forms. First, we define some additional types of dependencies. Inclusion dependency. The inclusion dependency has been designed for two specific types of database constraints that are not defined by the concept of FD, MVD and joint dependency. These two constraints are times foreign key constraints, times class-subclass relationships. Please note that these constraints are between two relations. Therefore, it requires a new form of formal definition. Dependency. These dependencies can define any constraints in the form of a template. A template consists of two parts. The first part, which shows the tuples that may exist in a relation, is called the hypotheses, which are followed by the conclusion of the template. A template dependency can be used to represent any dependency in this form. The following example shows how a FD can be represented using a template dependency. Example: consider a relation result, studented, coursed, grade, with the FD, studented, coursed grade. Represent this FD using template dependency. Description: studented, coursed, grade. Hypothesis: S1 C1 G1 S1 C1 G2. Conclusion: G1 is equal to G2. The following example shows how MVDs can be represented using template dependency. Example: consider a relation employee, EH, project, tool, with the set of MVDs, EH a project and EH a tool. The following template dependency defines these MVDs. Description: EH project tool. Hypothesis: E1 P1 T1 E1 P2 T2. Conclusion: E1 P1 T2 E1 P2 T1. One example of this MVD is shown with attribute values in the following table. Description: EH project tool. Hypothesis: E001 DBMS Python, E001 e-commerce virtualization. Conclusion: E001 DBMS virtualization, E001 e-commerce Python. However, the actual use of template dependency may be to represent the constraints that cannot be represented using FD, MVD and joint dependency. The following example explains this. Example: consider the relation EMP, MPID, MPName, salary, head ID. In this relation, the attribute head ID represents MPID of the head of the employee. You want to put a constraint in the relation that the employee cannot be given more salary than his/her head. The following template dependency would define this constraint. Description: MPID, MPName, salary, head ID. Hypothesis: E1 N1 S1 E2 E2 N2 S2 E3. Conclusion: S2 is equal to S1. The domain key normal form DKNF The domain key normal form, DKNF, is beyond 5NF and proposes to make a set of relations free of all anomalies. The DKNF was defined as a consequence of Fagin's theorem that states a relation is in DKNF if every constraint on the relation is a logical consequence of the definitions of keys and domains. Let us define the key terms used in the definition above, constraint, key and domain, in more detail. These terms were defined as follows. Keys can be either the primary keys or the candidate key. Let R be a relation schema with CKIR. A key CK requires that CK be a super key for schema R such that CKAR. Please note that a key declaration is a functional dependency, but not all functional dependencies are key declarations. Domain is the set of definitions of the contents of attributes and any limitations on the kind of data to be stored in the attribute. Let A be an attribute and DAM be a set of values. The domain declaration can be stated as AI DAM. It requires that the values of A in all the tuples of R be values from the set DAM. Constraint is a well-defined rule that is to be upheld by any set of legal data of R. A general constraint is defined as a predicate on the set of all the relations of a given schema. The MVDs, JDs are the examples of general constraints. However, a general constraint need not be just functional, multivalued, or join dependency. For example, the first two digits of your enrollment number represent the year in which you have taken admission. Assuming that MCA is the only program of the university whose maximum duration is 4 years. Also, assume that admission to this program was started in 2021. Therefore, in the year 2026, there would be two types of students, with students whose enrollment number starts with 21 and students whose registration number starts with 22, 23, 24, 25 and 26. The registration of the students whose registration starts with 21 would become invalid. Therefore, the general constraint for such a case may be, if the first two digits of T enrollment number is 21, then T marks are valid. The T represents a tuple and enrollment number and marks are the attributes. The constraint suggests that the database design is not in DKNF. To convert this design to DKNF design, you need two schemas as valid student schema is equal to enrollment number, subject, marks, invalid student schema is equal to enrollment number, subject, marks. Please note that the schema of valid students requires that the enrollment number of the students begin with 22. The resulting design is in DKNF. Although DKNF is an aim of a database designer, it may not be implemented in a practical design. 6.6 Summary. This unit explains the concept of multivalued dependencies, which causes a relation to have data redundancy. This causes a relation to have data anomalies. MVD is a consequence of having a set of attributes in a relation that determines more than one multivalued attribute, which are independent of each other. MVD forms the basis of decomposition of a relation into 4 NF relations. Further, certain relations do not have any FDs and MVDs but have anomalies. Such relations, in general, consist of more than 2 independent attributes. These relations contain joint dependency, that is, the relation has several projections which can be joined losslessly to produce original relation. The joint dependency forms the basis for 5NF decomposition. The unit also discusses about the inclusion and template dependencies, which are designed to represent the constraints that cannot be assigned using FDs, MVDs and join dependencies. Finally, the unit introduces the concept of DKNF. You may refer to the further readings for more details on these topics. Thank you for watching. We will see you in the next video with the next chapter.